What you're looking at is a complete hydrogen production facility. Most people think hydrogen comes from a single machine called an electrolyzer, but the reality is far more complex. Before hydrogen can be produced, water must be purified, electricity must be converted, gas must be processed, and pressure must be created for storage. Starting on the far left, raw water enters the plant and begins a journey through a series of hidden industrial systems. The water passes through purification equipment, power conversion equipment, hydrogen production equipment, gas processing equipment, compression equipment, and finally storage equipment. Each machine performs a specific task, and every machine depends on the one before it. Together, these systems transform ordinary water and electricity into one of the most promising energy carriers of the future. This schematic reveals the hidden machines behind hydrogen and shows how they work together as one integrated system. The journey begins with water. Although water may appear clean, it contains dissolved salts, minerals, organic compounds, and microscopic contaminants that are unacceptable for hydrogen production. This machine is the reverse osmosis, or RO system. The large horizontal vessels contain specialized membranes that act as molecular filters. High-pressure pumps force water through these membranes, allowing water molecules to pass while rejecting most contaminants. The stainless steel piping distributes flow throughout the system, while the control panel continuously monitors performance. The purpose of the RO system is to create a clean foundation for hydrogen production. Without this machine, contaminants would travel downstream and damage sensitive equipment. The glowing blue flow path illustrates the water entering the RO system as raw water and leaving significantly cleaner than before, ready for the next stage of purification. While the RO system removes the majority of impurities, hydrogen production requires water of exceptionally high purity. This is where the EDI system takes over. EDI stands for electro-deionization, a technology that combines electricity and ion exchange materials to remove the final traces of dissolved ions. Inside the vertical treatment modules, electrical forces continuously pull contaminants out of the water stream. Unlike traditional ion exchange systems, EDI continuously regenerates itself using electricity, eliminating the need for frequent chemical regeneration. The result is ultra-pure water suitable for electrolysis. The water entering this machine is already clean, but the water leaving it is refined to the standards required by the electrolyzer. This machine serves as the final purification checkpoint before hydrogen production can begin. Hydrogen production requires more than pure water. It also requires the right kind of electricity. Most electrical grids supply alternating current, commonly known as AC power. Electrolyzers, however, require direct current, or DC power. The rectifier performs this critical conversion. Inside this cabinet are sophisticated electrical components, including transformers, power electronics, cooling systems, control boards, and protection devices. Electricity enters the rectifier as AC power and leaves as stable DC power suitable for electrolysis. This machine is often overlooked, but it is one of the most important systems in the facility. Without it, the electrolyzer would be unable to operate. The rectifier serves as the electrical bridge between the power source and hydrogen production, ensuring that the energy entering the electrolyzer is stable, efficient, and precisely controlled. This is the heart of the hydrogen plant. The PEM electrolyzer is where hydrogen is actually produced. PEM stands for Proton Exchange Membrane, a technology that uses electricity to split water molecules into hydrogen and oxygen. Ultra-pure water enters the system from the EDI unit, while DC electricity enters from the rectifier. Inside the electrolyzer are advanced membranes, catalysts, bipolar plates, and flow channels that work together to drive the electrochemical reaction. Water molecules are separated into hydrogen and oxygen, converting electrical energy into chemical energy. The glowing blue pathways illustrate the movement of water, electricity, and hydrogen throughout the stack. Every machine before this point has been preparing inputs for this moment. The electrolyzer is the reason the facility exists. It is where hydrogen is born. Hydrogen leaving the electrolyzer is not yet ready for storage or transportation. It still contains moisture carried over from the electrolysis process. The gas-liquid separator removes this unwanted water. Inside the vertical vessel, flow conditions are carefully controlled so that liquid water naturally settles downward while hydrogen rises upward. Gravity performs much of the separation work. The visualization inside the vessel illustrates water collecting at the bottom, while hydrogen exits from the top. Although the separator appears simple compared to the electrolyzer, it performs a vital protective function. By removing bulk moisture, it protects downstream equipment and improves overall system efficiency. This machine represents the first cleanup stage in hydrogen processing. Even after separation, hydrogen still contains traces of moisture that must be removed. The hydrogen dryer performs this task. The two large towers visible in the system form a twin tower adsorption dryer. Inside each tower are specialized desiccant materials that capture water molecules from the gas stream. One tower actively dries hydrogen while the other regenerates, allowing continuous operation around the clock. Hydrogen enters the dryer carrying residual moisture and leaves as extremely dry gas suitable for storage, compression, and industrial applications. Moisture may seem insignificant, but even small amounts can affect equipment performance and reliability. This machine determines the final quality of hydrogen before compression. Hydrogen has one major challenge: it occupies a large amount of space. To store meaningful quantities efficiently, the gas must be compressed. This is the job of the hydrogen compressor. Inside this machine, hydrogen passes through multiple compression stages, with each stage increasing pressure, while cooling systems remove heat generated during compression. The large cylinders and piping networks visible on the machine represent the mechanical systems responsible for creating pressure. Compressing hydrogen is particularly challenging because hydrogen molecules are extremely small and difficult to contain. The compressor transforms low-pressure hydrogen into a practical energy carrier capable of storage and transportation. Without this machine, modern hydrogen infrastructure would be impossible. The hydrogen has now completed its production journey and arrives at the storage system. These high-pressure vessels act as energy reservoirs, safely holding compressed hydrogen until it is needed. The storage cylinders are designed to withstand extreme pressures while maintaining safety and reliability. Sensors continuously monitor pressure, temperature, and system conditions. The modular arrangement allows additional storage capacity to be added as demand grows. Storage is much more than a holding area. It allows hydrogen to be produced when energy is available and used when energy is required. This flexibility is one of hydrogen's greatest advantages as an energy carrier. The storage system represents the final destination within the production facility. The hydrogen journey is now complete. Water entered the plant as a raw resource. The RO system removed contaminants. The EDI system created ultra-pure water. The rectifier converted electricity into a usable form. The electrolyzer produced hydrogen. The separator removed bulk moisture. The dryer removed trace moisture. The compressor created pressure. The storage system held the finished product. This slide connects all those hidden machines to real-world applications. The hydrogen produced by these systems can power vehicles, support industrial processes, provide energy storage, and contribute to a cleaner energy future. What appears to be a simple fueling station actually represents the final connection between hidden industrial infrastructure and everyday life. This final schematic brings the entire hydrogen ecosystem together. Every machine shown throughout the presentation is connected into one integrated system. The RO system, EDI system, rectifier, electrolyzer, separator, dryer, compressor, storage system, and final applications are all part of a single engineering story. This is how engineers think about infrastructure, not as isolated pieces of equipment, but as connected systems working together toward a common objective. H2 Hub by Renee Energy was created to help students, engineers, professionals, and curious learners explore these systems in greater depth. By understanding the machines, components, and flow paths behind hydrogen production, it becomes possible to understand how real-world hydrogen projects are designed and operated. The goal is simple: follow the flow, understand the system, and discover the hidden machines behind hydrogen.